this session. This session, the speaker is Dr. Ratan Das. Already program is with you. Ratan Das, the youngest faculty of Department of Physics, Tripura University. In fact, I am glad to be here in this session because 2012, the year when Dr. Ratan Das joined Tripura University, and probably I was the Dean of Science during that period. So it is my privilege to find him with me in a session to give a short information about Dr. Das. He did his MSc and PhD from Assam University, Silchar. I found him active right from the beginning in the department, not only performing the regular classes, but also he is very much active in setting up laboratory. To say the laboratory in which he is working is a completely set up laboratory starting from 0 point. So he started from 0 point and up to the mark. What is the mark? The mark will say during his only 9-year periods in the department, he has conducted or communicated 55 publications in international journal and 6 in national journal. That is, publication is more biased towards international journal, I find. So it is a thanks to Ratan. And he is running 4 projects funded by various funding agencies of Government of India. And his work topic is mainly, he is doing work in nanoscience and nanotechnology with a lot of scholars with him, arranged by Department of Physics. So in this lecture, I would request all the participants, the recipients, to please follow his lecture. He will be giving some general idea about methodologies used in nanoscience and something which has been developed by him and communicated to others. And also, as usual, to interact with him via message box. I think no audio question because it will make some randomness in asking questions. So you please put the question in the message box and accordingly he will interact with you. So with this, I would request Dr. Ratan Das, please come to the presentation dais to start your presentation. Faculty attendants are eagerly waiting for you, sir.
Thank you very much, sir, for your kind introduction. And we need, especially me, need blessings from your side so that we can prosper further. And without wasting time, just I want to share my screen and start the lecture. Sir, just to confirm that whether my screen is visible and am I audible, sir?
No, I find screen is not visible.
I have shared it. Is it visible, sir?
No, till now I am not finding anything in the screen regarding your presentation.
Dr. Ratan, you unshare and then again share it. Oh,
Okay, I'm trying, sir.
oh now it's okay.
Okay, thank you.
Screen is visible right now.
Dr. Ratan. It's okay now. I am finding it's okay. I think participants which are now towards the listening will be finding this.
Okay, am I audible, sir, clearly?
Yes, I am finding you clearly audio.
Okay, sir. Thank you very much. Good afternoon, everyone, all the participants and the host and all the members. Today, I shall deliver a talk on the topic structural modification of a few semiconductor nanocrystals through swift heavy ion irradiation. So myself, Dr. Ratan Das, assistant professor from the Department of Physics. I established a lab in the name of Nanophysics and Nanotechnology Research Lab. So we are working on different types of nanomaterials. One aspect is that modification of especially the semiconductor nanocrystals to swift heavy ion irradiation. So in this aspects, I shall try to give some idea and about the research work, what is going on here, and hope that you may get some knowledge out of this lecture. Okay, so in the introduction part, I want to say that semiconductor nanocrystals from the large 2-3 decades has emerged as an important material, and its modification of that material is very necessary because we have seen that when we come down to the nanometer range, that semiconductor nanoparticle display different important optical and electronic properties because of the quantum confinement effect in the nanocrystals. Already you might have come to know, and many of us know that in the nanometer size range, that quantum confinement effect actually displaced by the nanocrystals and what is known as size dependent effect actually. So in this case, in this case of semiconductor nanocrystals, if we reduce the size, and then we find that structural changes we observe due to size also, and the structural properties of semiconductor nanocrystal is very significant. And if any subsequent modification take place, then it may helpful for us to engineer as per our wish the optical and electronic properties of semiconductor nanocrystals. Now, one way is ion irradiation method, or rather, I can say we can irradiate on the sample of low energy or maybe of high energy. Then this particular technique is very important to modify the sample without any physical damage or change in the sample. Okay. So as I told you that ion irradiation can be of low energy or high energy. So in the case of low energy, the ions get implanted in the sample, and thereby some modification takes place. And in the case of swift heavy ion irradiation, which is related to my topic, so in that case, that ion don't get implanted, it just passes through the sample, and thereby it modifies the things, and accordingly, which I shall try to communicate with you how this modification takes place actually. So ion radiation basically that has got tremendous response in the research community due to its ability to modify the structural part, and that depends on the type of the ion we use, or somebody use, the speed, incident energy associated with the ion actually. In swift heavy ion irradiation case, or in this method, that that electronic stopping power or electronic stopping that dominates over nuclear stopping actually. So basically, that swift heavy ion, that electronic excitation takes place when it passes through the sample, and that we shall see in the simulation in the next slide. And that swift heavy ion radiation with very huge energy that can be produced in an accelerator and with very high energies, typically in the MeV range. But in the low energy irradiation, that energy may be in keV range. Okay. But maybe you may get in the low energy part 1 MeV or 2 MeV. But here in the case of high energy swift heavy ion radiation case, that MeV may be up to 200 energy level or MeV range. So in this case, what happens that when an ion passes through the sample, it just releases sufficient energy to induce some permanent damage or modification in the system, and thereby through its passage it creates a cylindrical zone, what is called ion tracks. The ion tracks is not a cylindrical path actually. It is a path obviously, but it is not a hole like things. But while the swift heavy ion passes through the sample, through this ion track, the modification actually takes place. So different ions going through the different paths, and then the modification will take place through this path actually. Now, among the different types of nanoparticles, I have chosen here CDS and CDS because these are very important and well-known group 2,6 semiconductor nanocrystals from the application point of view, because CDSC and CDS, as you know, that they have tremendous application starting from solar cell to different types of electronics application part and display material. So in many different important technological purpose, we use CDS and CDS. That's why I have chosen this material. Okay, and they generally possess the cubic and hexagonal lattice structure based on the method of synthesis, because we may prepare the sample by different synthesis method. So generally they display cubic and hexagonal lattice structures. So in this work, the CDSC and CDS nanocrystals that I have chosen have been prepared through a wet chemical method, and that morphological characterization have been performed using SEM and F and TEM also, but I haven't included here the TEM. The structural properties of the sample been studied by XRD and Raman spectrum. Optical properties, as usual, by UV visible spectrophotometer absorption and emission study we have done through it. So what is that swift heavy ion radiation? This is a technique used for manipulating the material at the nanoscale, as I have told you, without damaging the sample. This is the advantage actually. But at very high fluence, or at the highest fluence, the sample may get damaged. But you have to understand the fact that you have to irradiate the sample below that particular range. Okay, in that case, the modification will take place without any damaging the sample, and the modification, as usual, we cannot do without that irradiation method actually. So during the irradiation, what happens that swift heavy ions deposits substantial quantities of energy, as I told you, to the system, and or rather I can say the target material, which happens in the case of picosecond time scale. Okay, it is not a very long duration process, but in the particular process takes place in the picosecond time scale. That's very important. Okay. And this result, that particular modification that results in electronic excitation, or the process results in electronic excitation and ionization as well. And thereby it modifies the interatomic forces and lead to permanent atomic displacement, right? So while passing through the sample, the electronic excitation takes place, and thereby the excited electrons or ionized electron, they may interact with the.
Sir, your voice is breaking, sir. Please, your voice is not clear.
Okay. Sir, am I audible?
Sir, you are audible, sir.
Okay. So what happens that the excited electrons or ionized electrons, they actually interact with the sample or other atoms or other electrons, and they lead to permanent atomic displacement. Okay, what we can say that that some sort of defects or some sort of arrangement in the structure takes place. Okay, so as I say, irradiation in this way forms a cylindrical damage zones of diameter in the nanometer range that I shall explain little bit in the subsequent slides. What is known as ion tracks, as I have mentioned you earlier also, along the linear trajectory of the ions. So depending on the materials and the distribution of defects due to irradiation, variety of phenomenon that may take place, or we can experience such sort of things like phase transformation or amorphization, which directly modifies the different microstructural parameters such as grain size, intrinsic strain, dislocation density, etc. Now, due to irradiation, what happens that sometimes a material which is crystalline in nature, it may become crystalline again after irradiation, but of different structure, maybe cubic to hexagonal, that what we have experienced in our case. Or it may happen that the crystalline to amorphous materials, it may convert, or that conversion takes place due to irradiation. Or it may happen that amorphous to crystalline states, it may go. So in a very easy way, you cannot do this, okay, without such sort of method, because amorphous to crystalline material, you cannot transfer a particular sample without damaging it until and unless you irradiate the sample with swift heavy ion. So this is a very good technique that without damaging the sample, we may convert our sample to crystalline phase, or crystalline to amorphous phase, or amorphous to crystalline phase as per our need. So that is the beauty of swift heavy ion irradiation actually. Now this particular irradiation facility is there only at IUSC New Delhi, because swift heavy ion irradiation requires a special type of accelerator, what is there in 15 UD Peloton tandem electrostatic accelerator, which is a pentagraph generator type accelerator. Okay, so the picture displays that the huge part is where inside that part there is an accelerator. And I can just share one thing, that there is a car there in the building. We can just compare with this particular scale, that how big that particular accelerator. Okay, so they are actually just above the people or operator. They reach there and they just start sending with some technical use. They send the required ion, and through the pentagraph generator, it gets accelerated, and we obtain huge energetic ion actually. So the energy may reach up to 200 MeV depending on the ion species. Okay, so there are some ions that I have listed here, but a few ions that I have come to know that these are available at their IUSC New Delhi. I have used nickel and Ag ions for my sample, and I have used 120 MeV nickel and 10 plus ions and Ag7 plus ions, okay, for the irradiation purpose. Now, how can we choose that particular energy and particular sample actually? This is something that comes after doing some literature survey or after getting some experience. But right away, just I want to say that there is a simulation, what is known as stream team simulation. In that simulation, we just use a target material and we use a particular energy source, whether it may be silver, whether it may be nickel, whether it may be cobalt, or any other source we may use, and then we just get different parameters out of that simulation process. And what happens that this simulation process, if we plot all the data, then we see that this is the electronic energy loss, okay, which is going through this line, the black in color, this is, and red in color. These are nothing but the that electronic energy loss. Okay, so with the incident energy, if we increase the incident energy, the electronic energy loss is increasing. But the green and the blue part is their nuclear energy loss part. So we can see from the simulation that that nuclear energy loss part is very small, and the electronic energy loss is very high in that case, in the case of our sample and other things. But sometimes what happens that people need a particular sample or particular ion where that nuclear energy loss may be higher. But in our case, we have found that the electronic energy loss is very higher, and this signifies that that whenever that particular Ag ion that I have chosen or nickel ion, which when passed through the sample, it excites the electron, or it never interacts that much with the nucleus in the system, in the atoms. Actually, it excites the electron, and thereby electronic energy loss takes place. What is that electronic energy loss? Is that to the electron, the heavy swift heavy ion just transfer the energy, and that electron get excited, or it may get ionized, and thereby it hampers, or rather I can say it just modify the sample accordingly by interacting with different atoms and electrons there in the sample actually. So this simulation is very important before going the experimental part, because you have to know what is going on in the sample out of that simulation actually. Okay. Now this is the stream actually. The stream is nothing but stopping and range of ion in matter. This is a package, and this is a numerical simulator, and we can get this simulation out of these things. And after doing this, actually, we can go after, or we can propose that we need that sample, we need the things, because these are the outcome of that simulation. And by this, we can then go after a particular experiment, because this swift heavy ion radiation method process is very costly actually. You know, no one can get easily that particular thing. So you have to get the things. Yes, it is a UGC funded established institute, but still you cannot avail the things easily until and unless your work is very significant. But you have to propose a work there, and then if you are your work is good enough, or your idea is good enough, then you can easily get the ion radiation or the beam time, that I can say. Now in the stream we can get these things, that whether it is a electronic energy loss or nuclear energy loss is taking place. You see in the simulation we have found that the electronic energy loss is higher for Ag actually. The black one is for Ag, and the red one is for nickel. So in the sample of CDS, we have found that silver, for the case of silver ions, the electronic energy loss is higher compared to the nickel ion. Similarly, also in the case of CDSC, we have found that electronic energy loss for silver ion is more than the nickel ion. Now, in the case of stream, simulation, what happens that we may obtain particular parameter, what is known as displacement damage, and this is that, or rather I can say that how much depth we can go with a particular energy ion. So here we can see that the depth is around 10 micrometer. So in that range, up to that range, that one particular sample the ions can enter or penetrate or modify the sample, or displacement damage takes place up to that particular range. So getting this particular information, you have to prepare a thin film out of your sample below the range of that particular displacement damage process up to which depth it takes place actually. So in my case, it is 10 micrometers. So you have to prepare the sample below that particular that depth actually. So below the 10 micrometer, you have to prepare a thin film. You cannot make a very thick film. In that case, that otherwise either the upper part will be modified, lower part may not get modified in the sample. So these things are there. That's why you have to do the trim simulation, and you can get that sort of profile, and out of this you can get information and some sort of experience that how much thick or how much thin should be your sample actually. So that particular process or that simulation process actually based on Kin-Thin piece model. Okay, I don't want to say about all these things, but what happens that for a particular sample, for a particular energy level, for a particular energy of that ion that you have chosen, you have to know the displacement damage profile beforehand using the trim simulation. Okay, so with this information, what happens that we have prepared the CDSC and CDS nanocrystals with following some established chemical process, so that is not a very difficult task. But we have prepared CDSC and CDS nanocrystals out of some established chemical process. We have synthesized the samples, and then we have prepared the thin film out of that prepared sample with spin coater, or you may cast the sample so that at least the thickness is below 10 micrometer as for my case, and we have dried that sample in the normal temperature. So this is the simulation, the displacement damage for that CDS and CDSC nanocrystals, and we have already found that it is below 10 micrometer, and this is for CDSC also it is 10 micrometers. So we have prepared accordingly the sample. We have prepared a thin film out of our prepared synthesized nanocrystals, and then we have started irradiating the sample with swift heavy ions of Ag and nickel ions of at least 120 MeV energy. So we have arranged that part. We have gone there and we have used that things. Now after irradiation, we may see whether our crystalline sample, how much it get modified. So the morphological analysis will give you an idea about that how much your sample get modified after irradiation. But if you irradiate the sample with very high energy, it may get damaged. So you have to think about that, and you have to find out the way how not to damage the sample actually. Okay, so the crystalline sample before irradiation, we have taken the same image, and we have found that the average size is around 25.70. Okay, around 26 nanometer. But after irradiation, we have seen that that the irradiated sample, the average size is around 32, right? And here also we can see that Here also we can see that yes, it is not visible though, but that it is the size must increases actually. So here from 25 nanometer to we have increased the size up to 32 nanometer. Okay, so for C we have irradiated the sample with nickel ions, but the fluence may be different. The fluence we have used of 1 into 10 to the power 11, 3 into 10 to the power 11, then 3 into 10 to the power 13 ions per centimeter square. So at the highest fluence of nickel and Ag, it has been observed that average particle size increases after SHI irradiation from pristine CDSC. So overall, the average size increases after irradiation actually. Okay. And this is the effect of irradiation on CTS nanocrystals. So pristine is 12.55 nanometer around, and after irradiation we have found it is 14 nanometer and 16 nanometer. With 120 MeV nickel ion irradiation, the size increases up to 14 nanometer, and with silver ions the size increases up to 16 nanometer. So what is the difference? Because of this, the difference we have observed that due to nickel ion irradiation, the size is not that much increases average size, but the silver ion actually, what does the silver ions, which increases the average size up to 16.8 nanometer. This may be related to the fact that of that electronic energy loss is higher for silver ion, and which interacts the sample, or it delivers the more energy to the sample. Okay, and thereby the agglomeration or the sort of things, whatever happens there to increase the size, it takes place much more for silver ion than nickel ion actually. That's why we have found that for silver ion, 120 MeV silver ion irradiation, both for CDSC and CDS, the size is much more than nickel ion irradiation. Okay. Now, in the case of AFM study, also we have seen that this is the pristine sample, and we have calculated the roughness. Average roughness is around 3.6 nanometer. And after irradiation, that 120 MeV nickel ion irradiation sample, we have seen that the texture, waviness, and roughness is much different from the pristine sample actually. Okay, so that indicates that even the surface of the thin film gets modified. The FM study indicates that surface also get modified due to the irradiation. So you can use the swift heavy ion irradiation for the surface modification purpose even. But as we are interested in structural modification, we can see how the structure gets modified, and how much defects or dislocation density gets created after SHI irradiation, right? So X-ray diffraction pattern is an important tool through which we can analyze the sample, especially for whether any structural modification structural modification takes place or not. That we can study from the X-ray diffraction pattern. Okay. So in the X-ray diffraction pattern, as the CTS nanocrystals, as I have told you, that sometimes it shows cubic structure or hexagonal structure. So in our case, we have observed that that a prepared pristine sample is cubic in nature. CDSC is cubic structure, and its peaks have been observed at 1, 1 and 200. Okay, at different corresponding angles, theta angles. We have observed this sort of peaks, and that indicates that it is a FCC cubic phase of the CTS nanocrystals as per ICDD software or JCPDS software. Now, after irradiation, this is very important so far as our study is concerned, or any particular study is concerned. That as I have told you, have used different fluence of particular ion. So here I have used 10 to the power 11 ions per centimeter. This is the fluence of silver and nickel. 10 to the power 13 also I have used, and 3 into 10 to the power 13 we have just used these samples. Now the pristine sample is cubic, and after irradiation of 1 into 10 to the power 11 ions, then we have observed that some distortion is taking place in the cubic phase with the appearance of new peak 101 peak is there. Okay, so after now this is one sample with irradiation of 10 to the power 11, and then again at the influence of 10 to the power 13 ions, we much more modification in the peak 11 peak has been observed actually. Okay, and here also in the case of these peaks, the modification is taking place. So this indicates that if we increase the fluence, and then some sort of modification is taking place actually. It is not that in situ experiment, but I have a sample of 10 to the power 11 ions. Okay. So 10 to the power at the 10 to the power 13 ions, we have seen more modification in the sample actually. So this particular sample at 10 to the power 11 ions per centimeter, some little bit modification has been observed. With increase in ion fluence, more modification has been observed. But at the ion fluence, the highest ion fluence of 3 into 10 to the power 13 ions, the total phase change has been observed, because all these peaks correspond to the hexagonal phase actually of CDS. Okay, this is very important, because with the ion irradiation, we have just transferred the sample from cubic to hexagonal without damaging the sample actually. So the intensity of cubic 11 peak starts to diminish, and the appearance of new peaks has been observed. Okay, at the maximum fluence 3 into 10 to the power 13 ions per centimeter, the cubic peaks this cubic peak disappears, and new peaks appeared at the corresponding angles of 23.21 theta angles, and the new peaks 100, 002, 101, and these sort of peaks that corresponds to the hexagonal phase of CDSC actually. So with 120 MeP nickel 10 plus swift heavy ion irradiation at the ion fluence of 3 into 10 to the power 13 ions per centimeter square, the cubic CDSC totally transferred into the hexagonal phase. But we do not know whether that transformation is 100% or 90% or 80%. We do not know. It may happen that 100% transformation takes place. It may happen that 95% or 95% transformation takes place. Then we shall study that how much fraction of hexagonal phase actually that gets transferred or transformed due to this SHI irradiation actually. Similarly, in the case of 120 MeP Ag7 plus ions, we have observed similar, almost similar sort of transformation from cubic to hexagonal, but as the electronic energy loss is more for silver ions, but so we have observed some changes in the intensity of the peaks. Intensity of the peaks is different, as well as shifting of the peaks is also different compared to the nickel ion actually. Okay, so this change may be because can be attributed to the different electronic energy loss by nickel and silver ions, and this can be studied in the kinetics of phase transformation of CDSC nanocrystals. Similarly, for CDS nanocrystals also we have observed some sort of things. Okay. Now, what happens that as 1,1 peak is very a major peak, it is the major peak in the it is a major peak in the cubic phase. So we have considered that 1,1 peak only, and the 1,1 peak of that pristine sample. This is the replacement of 1,1 peak by these 3 peaks in the hexagonal phase. Okay, and this 1,1 peak then is there after that 10 to the power 11 ions per centimeter fluence of nickel. And similarly, we have observed that things for silver ions, and that this sort of phenomenon we have observed in the case of 1,1 peak with different ion fluence. And why I am showing this particular 1,1 peak, because now we shall considering this particular 1,1 peak, we may study the fraction of hexagonal shift or hexagonal transformation in the sample actually that we shall study. That's why we have considered here the 1,1 peak only, and the intensity of 1,1 peak for nickel ion irradiation, for silver ion irradiation, that intensity we may just observe, and at the highest fluence we may observe the hexagonal peak intensities. And by measuring the intensity of the peaks of different irradiated sample, we may try to find out the fraction of hexagonal phase that takes place, or that gives us a quantitative analysis of the fraction of hexagonal phase, which is different from cubic phase. Okay, cubic phase are our pristine phase, and irradiated phase is hexagonal phase, or transform phase is hexagonal phase. So there is a model, what is called the Garbian-Nicholson model. As per this model, the fraction of hexagonal phase is given by this particular formula, where that 100, 002, and 101, these are nothing but the peaks of hexagonal phase in the place of 111 peak. So this is the hexagonal peak intensity additional. We just added this all the peak intensity, and this is the peak intensity of cubic phase and hexagonal phase. And this way we can get the fraction of hexagonal phase actually. Now taking this hexagonal phase, or taking this hexagonal that fraction of hexagonal phase, we may just plot or go for a particular model, what is known as double impact model, or we may go also for we may use the single impact model, but in the case of double impact model, this is the formula actually, and here that sigma A corresponds to the cross sectional area of the cylindrical tract that actually produced by the swift heavy ion irradiation while going through the sample actually. And we may just plot this, and we may just plot our fraction of hexagonal phase, and we use this model. And here what happens that the peak integrals of XRD-PX have been calculated using the baseline method after background correction, and the shape of the peaks is taken as Boyd function. And by plotting, or just by best fit of the observed fraction, and from the best fit analysis, we can find out the radius of the ion track. Okay, it is the R square value is 0.82, so it is very good fit. It indicates, and what happens that in the case of a single impact model, because single impact model is that only single ion is triggering the phase transformation, but double impact model is the fact that where the two ions is triggering the phase transformation. Double impact model actually consider the phase transformation as two-step process, where the first ion creates enough SHI induced stress to the lattice structure, and the second ion immediately triggers the local structural modification. Okay, and thereby yielding a cubic to hexagonal phase transformation of CDSC nanocrystals. Okay, so the ion tracks has been determined from the fit, and that has been that gives us the ion track as 2.86 nanometer for nickel irradiated CDSC and 2.92 for AG irradiated CDSC. As it is higher, 2.92 is higher. So obviously that may be attributed to the higher electronic energy loss by silver ion. Okay, so as this result shows that AG ion produces larger track radius than that due to nickel ion actually. Okay, this is the overall that changes in the peaks that takes place due to the different fluence of SHI irradiation. And similarly for this is for CDS sample, and we considering the 1 peak again, we have we can calculate or the calculated track radius is 2.78 for nickel irradiated sample in the case of CDS, and 2.9 nanometer for silver irradiated sample. Okay, so what is the explanation of the ion track radius? Actually, I should have shown you the graphical mode of this ion track radius actually, but I did not go to that particular part because this is a different slide. But simply I can say that the formation of ion tracks along the path of the ions can be explained with thermal spike actually, and SHI that affects the local structure of the material and creates cylindrical tracks in the sample. This is as simple. But during the passage of the SHI, as I have told you that this is a picosecond phenomena. So electronic energy loss of the ion leads to excitation of nearby electrons, which starts then interacting with the local atom that I have told you earlier, and thereby it transfers all the energy to the lattice side through electron lattice interaction. Thereby it transfers the whole energy to the lattice sides, and the lattice some sort of oscillation takes place as per thermal spike model, which displaces several ions, and thereby it creates defects, it creates dislocation density, etc. in the sample, and thereby what should I say, that because of that displacement, the bond breaking phenomenon along the certain collective atomic arrangement starts in the crystals. Okay, this process induces very high temperature increase, or the temperature increase very high order that takes place in the sample. And that takes place within a very short time. It is in picosecond time interval. I have not written here though, but it is picosecond time interval that sort of things takes place, and elevation of high temperature takes place. And because of that, local heating and melting of the local lattice structure leads to the phase transformation. Actually, we do not experience this melting of local lattice structure and rearrangement, because it is that takes place in a very short interval of time in the picosecond range. Just simply we observe later that sort of things that happens, that phase transformation that happens. But as per thermal spike model, that it induces all sort of things, and temperature increases, melting takes place, and realignment takes place, but that takes place not throughout the sample, but along the cylindrical ion track along which the ion is passing through actually. Now let me go to the X-ray diffraction peak analysis. It is very simple, as many researchers do this peak analysis. So the peak analysis actually, as for an ideal crystal, as the XRD peak should be a delta function, as you know it very. Most of the participants know these things. But in real crystal, many factors affect the diffraction peaks, and it broadens actually with peak shift and peak asymmetries appears in the sample after irradiation or in the crystalline sample even in the real crystals. Okay, so we do the peak profile analysis through the measurement of Fullerton half maxima or through Fourier coefficient analysis method. Here we did not touch upon the Fourier coefficient analysis part because this is something different we are doing. But simply I have confined to the Fullerton half maxima analysis actually. So what happens that just simply, as we know, this is a very basic things that the XRD peak for an ideal case, it should be a delta function. But broadening takes place because of the crystalline size, the strain, or the defects. But there are the instrumental broadening also, but which we can get rid of after some correction. Okay, we may get correction of the instrumental broadening, but there are some defects taking for strain, crystalline size. There's contribute to the XRD line broadening actually. Okay, so this simply we can calculate the size out of that Scharer formula. This is based on the size effect actually. This is very simple thing, but there may be introduction of intrinsic strain in the sample, which may also give rise to the broadening of the XRD peak. And this that intrinsic strain can be obtained from different method: Williamson-Hall, Helder-Wagner, sustain plot, Warren-Barberg, Boyd method. Different methods are there, and we can use these things for our analysis part of finding out the strain and the size. So based on the broadening of XRD peak, that Williamson-Hall, the Helder-Wagner method, Barron's method, these are the methods we have used. All these are not here, but the broadening or whether I can say based on the Fullerton half maxima, we do consider this sort of analysis method. But we have also used the Fourier coefficient of XRD peak, and the analysis part is Warren-Barberg method and Balzer method. Here that part I did not include it in this particular topic, but we shall simply discuss some Williamson-Hall method here actually. So we may get rid of the instrumental broadening by considering a standard sample, and we may calculate the size even, but strain part is 4 epsilon 10 theta that Stokes considered the deformation due to strain, and it is there. So if we combine these two things, we may obtain the broadening phenomenon that takes place due to the size and the strain as well. So in the classical Williamson-Hall method, what happens that the peak broadening is the combined effect of size-induced broadening and strain-induced broadening actually, after getting rid of the instrumental broadening. Okay, so what happens that the corrected total broadening of different diffraction plane can be written as this FK scale is the actually the Fullerton half maxima corresponding to a particular plane, and it is there that the size part is there, strain part is there. Now if we just put k is equal to 2 into sin theta by lambda, this put if we take as k, then delta k will be this f scale cos theta by lambda. So delta this particular expression can be written as delta k 0.9 by d twice epsilon k. So this is the simple, very simple. Many of you know probably the classical Williamson full equation, and this shows that from the plot of that particular equation, we may obtain the size from the intercept and the strain from the slope actually. So average size of the situation nanocrystal has been determined from the intercept and the plot as 28.12 nanometer. Okay, and this is as per our SEM analysis also. And this is the irrigated sample, and we have seen that after calculation as per classical Williamson-Hole method, the size increases. From this analysis also, we have found that size increases, and this is as per the experimental SAM analysis, where we have seen that both the nickel and silver ion, after nickel and silver ion irradiation, the size increases. Here also we have observed that from the XRD analysis that size increases after irradiation also. Okay. And the strain also has been found to increase for nickel and silver ion as well. So this is the Williamson-Hole analysis of CDS nanocrystals, and similarly here also we have observed increase in size actually and increase in strain even. Don't want to go into the deep, but saying as overall. That the classical Williamson-Hole is a very simple thing, but we are correlating the effect of irradiation here with the observed experimental fact of SAM actually. Now, what happens that this particular classical Williamson-Hole actually based on that isotropic strain actually means in every direction the strain is same actually. Okay. It is not anisotropic, but there is a modified Williamson-Hole method where we do consider the anisotropic strain along different crystallographic direction. Okay, there is the difference of the modified Williamson-Hole from the classical Williamson-Hole. That classical Williamson-Hole method assumes the isotropic strain broadening, but modified Williamson-Hole actually considers the anisotropic strain broadening because of the presence of different defects or dislocation density, and because of the presence of different defects and dislocation density, actually it affects the strain, or we can say the strain become anisotropic in different directions. So according to that MWH method or modified Williamson-Hole method, this anisotropic strain can be characterized by anisotropic contrast factor. This is a factor actually, and where the dislocation density is defined as the source of anisotropic strain actually. So what is the source of anisotropic strain? It is nothing but the dislocation density, because the ion irradiation here, I want to say you, because of the irradiated sample, what happens that in the crystalline sample that may happen in the real crystal, but in the case of ion irradiated sample, what happens that the passage of the ions may create different types of defects, the damage it takes place, thereby some sort of dislocation of atoms takes place, and there we may find out different types of dislocations, whether it is S dislocation or screw dislocation, that sort of things we may observe. But density, that sort of dislocation density that appears in the sample, it may be the source of the anisotropic strain. With this consideration, the classical Williamson-Hole can be written as, you see, the second part is different from the modified from the classical Williamson-Hole plot. The first part 0.9D is remains same, but the second part twice epsilon k, it is different for the modified Williamson-Hole method, where we have considered anisotropic contrast factor C, and where we have considered that dislocation density is the source of anisotropic strain. Now beta is a parameter, it is a dislocation parameter, and it is related to B square and sigma. The sigma is the dislocation density and B is the Barger vector actually. That Barger vector is very important because I don't want to go into the details of all these things because because of the time limit I cannot say all these things, but I want to say that Barger vector is very important because it gives whether the dislocation density is screw type or S type or mixed type. Okay, and O stands for the higher order of this particular factors of anisotropic construct factor actually, which we may neglect for numerical convenience, but we just simply will consider the first two terms. This is the size term that is there in the classical Williamson whole part, but this is the part that there because of the presence of anisotropic strain. Now, from the literature, as it is considered that for cubic FCC structure, the value of Berger vector B is considered as a by 2 for 100 plane, where it is in the direction, okay, and where A is the lattice constant of the crystals. And what happens that that occurrence of different types of dislocation actually is related to the orientation of the Berger vector, as I told you, and the dislocation lines. And it actually depends whether the Berger vector is perpendicular, parallel, or in arbitrary direction with respect to the dislocation line, and dislocation line is there in the dislocation part, and depending on that factor, we may define whether the dislocation is edge, screw, or mixed type of dislocation actually. Okay, so if we then go further, then this anisotropic contact factor is related to the geometry, lattice geometry. And that lattice geometry, because it is related to H square, and H square is related to the lattice geometry because it is related to the Miller indices, and the CH00 is the average contrast factor along a particular direction H00. This is the preferred direction that we have considered actually, and Q is a parameter that depends on the character of dislocations, whether it is a screw, whether it is a edge, or it is a mixed type. Okay. Now that based on that diffraction plane, the value of H square can be obtained corresponding to the diffraction plane, whether it is 111 or that 222, that sort of things. And CH00 and Q, it has been considered from the literature because it is difficult to calculate, and we have just taken it from the literature for the determination of the contrast factor C and Kc half. As per a modified Williamson whole, that the term Kc half has been plotted and against delta K, and from the plot the average size has been observed at 27.7, whereas dislocation density is 1 into 10 to the power 14 per meter square. Okay, so this particular size that we have obtained from modified Williamson whole method, it is as per the same analysis again. Okay, but advantage of this particular method is that we can find out or we may calculate the different dislocation density. Okay, now for irradiated sample, we have seen that after calculation for this particular true part of irradiated sample, we have observed an increase in average size as well as increase in dislocation density. I haven't included it here, but dislocation density has been found to increase. A significant increase from 10 to the power 14 to the power 15 takes place due to the irradiation method. Okay. And similarly for CDS nanocrystals, the size also increases as has been observed or calculated from modified Williamson whole method, which is as per the same start. Now that both the classical and the modified Williamson whole analysis confirm that that the parameter of semiconductor nanocrystals, different crystallographic parameters of semiconductor nanocrystals get modified after the SHI irradiation, and this can be understood from the thermal spike model. Okay, as per which I have told you that that as per thermal spike model, the ions deposit huge enough energy to the local sites along the path, and this induce some electronic excitation in the material and transfers energy. It just produces different defects in the sample, and as well as phase transformation takes place, modification of local strains, so many things takes place, and we can find out all these things, the lattice strain, dislocation density, whatever they are, from the XRD analysis. So XRD analysis is very important tool which we can use for this sort of modification, whatever that takes place after irradiation in the sample. Okay. Now, what we did that that the XRD pattern of the crystalline sample and the irradiated sample, we went for the Rydberg refinement. Okay, and after doing the Rydberg refinement, we have found it very well matched with whatever we can say that the chi-square value is very small. It is near about 1, so it is giving a very good fit. And from the Rydberg refinement, we can obtain different parameters actually. It is also showing from that part also that cubic to hexagonal that phase transformation takes place, and we can calculate different lattice parameter there in the sample actually. Okay. Now what we did that because we can obtain some crystallographic information, crystallographic data from this Rydberg refinement, and we can use it further. It is not a general idea that simply we can do the Rydberg refinement whether it is matching or not, but not like that. But we did with some purpose. We did the Rydberg refinement with the purpose that we need the CIF file actually for getting precise structural information of the phase transformed structure. Okay, and we did the same thing for the case of CDS nanocrystals. Okay, the background is very small. So whatever the Rydberg refinement is giving us almost a very best fit, and the CIF file is almost correct. And what happens that thereafter we may okay. Yeah, just let me finish that part, and I shall tell you that what is the importance of Rydberg refinement. Okay, let me go to the Raman analysis. We did the XRD analysis, and we did thereafter the Raman analysis of the irradiated sample. That Raman analysis we did at IUSC itself. It is there. The micro Raman instrument is there. Micro Raman spectroscopy is there. So this is an effective micro Raman spectroscopy is an effective method in obtaining information about the lattice distortion or lattice structural information can be obtained from this particular Raman analysis. So the evolution of the structural damage in the prepared nanocrystal also has been studied from the Raman spectral analysis. What happens that in the Raman spectra we have observed the yellow peak and the twice yellow peak, and that corresponds to the longitudinal optical phonon mode and the second order optical phonon mode, which has been observed at 210 centimeter per inverse and 411 centimeter inverse. Modes are represented at that particular value. Okay. Now, what indicates that this is the characteristic peaks corresponding to the CDSC nanocrystals, and in the case of a bulk sample, actually that yellow modes appears at 212 centimeter per inverse. Okay, and this there is a shift of around 2 centimeter inverse redshift obviously in the yellow mode when we go down to the nanometer range. So this shift actually because of the size confinement from the bulk sample. From the literature we have observed that it is there at 212, but our observation is at 210. So the first LOP, and that indicates the confinement effect or the size effect in the nanometer range. Okay. So what happens that after irradiation at different fluence, we have observed evolution of the Raman peak. Okay. So if we go from pristine to the first irradiation 110 to the power 11, then what happens that the peak has been found to increase. Okay, intensity increases up to the 10 to the power 13 ion per centimeter square. But at 3 into 10 to the power 13 square, the peak intensity decreases much compared to the pristine sample or compared to the 10 to the power 13 sample, which indicates the damaging of the sample or presence of some distortion, which indicates the huge dislocation density, the presence of dislocation density in the sample actually. Okay, so we have observed the peak shift from 210 to 208, then 209, and then 206. Okay, so this sort of peak shift has been also observed. So the observation is that at the maximum fluence, the intensity of yellow peak decreases considerably. Okay, and this increase in yellow peak may be attributed to the slight change in geometry, but at higher fluence, due to the change of cubic to hexagonal phase transformation, because of this lattice structural distortion due to swept heavy ions, the peak actually decreases. Okay. Similarly, we have observed for AG ions also, and from the plane of plane stress model, rather I can say, we have calculated the stress actually, and that standard stress actually increases accordingly with the irradiation both for silver and nickel ion from the crystalline sample. You see the tensile stress increases much with irradiation. So similarly, we have observed for CDS sample as well. Okay. So this dynamics of damage fraction propagation can be understood from the change in the relative intensity of yellow peak with ion fluence with respect to the crystalline sample actually. Okay. So similarly here for CDS also we have observed the increase in tensile stress. Okay. So this may be the tensile stress can be attributed to the high deposition of energy to the to the sample due to the ions. But it is the increase the mass. It is much higher for silver ions compared to the nickel ions actually. Now, we did some first principle study, the DFT based study. And here we did not, as many of you know, the first principle study, the optimization is required for any particular sample or any particular consideration of structure. But here, what we did that we did a trick that from the read belt refinement data, we have taken the CIF file. Okay, we have taken the CIF file. And yes, we have taken this CIF file from the piston data and from the irritated data, and we directly fed into the first principle study where we have used the quantum espresso code and we have used the PB as a XC functional. Okay, by feeding the same file and considering all the parameters, and we have just found some band gap modification. This is the band structures, and these band structures indicate that yes, obviously that CD, SE, and CDS are direct band gap materials. So this indicates direct band gap material. And what we have seen that the piston sample giving us the band gap of around 2.02, but it is decreasing in the case of nickel irradiated sample, and as irradiated sample, it is decreases much. The decrease is much more for AG irradiated sample, where we have used the PV plus U functional for both the case. Okay, so what happens that we have observed some modification in the band structures, and similarly in the DOS study, density of state study, we have observed the band gap modification due to the irradiated sample compared to the piston sample, where it is 2.02, but it is much lower compared to the piston sample. And this is for piston CDS and irradiated CDS, where we have observed again the decrease in the band gap. Okay. Now we have in the DFT analysis, we have taken the charge density plot, and we have observed that some changes in the charge density that takes place. This is the piston sample, this is the irritated sample, and that clearly indicates after feeding the CIF file, because CIF files are nothing but corresponds to the XRD pattern of irradiated sample and piston sample. So this is the direct observation. The CIF file is nothing but a direct observation of experiment, and using that experimental facts, we are feeding into the theoretical simulation part, and this is displaying a fact that that the charge density is getting distorted after irradiation. So this displays this is one way we can say we are correlating the experiment with the theory, and it is indicating the theory is also indicating or the simulation analysis indicating yes, there is changes in the charge density. It is because of the we can say that electronic charge density is getting changed due to irradiation. As we know, the structural orientation has taken place because of the irradiation effect, or charge transfer phenomenon has taken place due to structural modification. Okay. So we have observed there is some homogeneity we can observe, but here is some inhomogeneity we have observed in the case of irradiated sample. This is the theory part. Now let me go to the experimental part again, relating to the optical study, and we have taken the absorption spectra of both irradiated sample and the piston sample, and there also from the Tox plot we have observed some changes in the band gap from 2.26 electron volt to 2 electron volt. Okay, so this is not exactly matching with that sort of exactly it is not matching with the theory, because theory is something different based on some assumptions, but experimental fact is giving another values. Okay, so we have observed the relation is that we have observed decrease in the band gap, and in the theory also in the simulation part from DFT analysis we have observed decrease in the band gap. So this is the main actually the idea that how can this experimental results relates with the theory. Okay. And this is again for CDS nanocrystals. Here also we have observed the decrease in the band gap as that has been observed in the GIS and the density of states or band gap analysis from irradiated sample in the case of DFT analysis. Now, what happens that from that optical property study we can calculate the refractive index and dielectric constant, which is related to the energy band gap, and from here we can calculate directly the refractive index, and thereafter the dielectric constant. The refractive index has been found to be higher, and dielectric constant is also found to be higher. Now, refractive index is found to be higher because this is the piston sample. You see, it is 2.26, and for irradiated sample, where it is band gap, 2.63, and it is for irradiated sample. Okay, and 2.60 to 2.65 that sort of increase in refractive index takes place, and that at 3 into 10 to the power 13. 2.71 value it reaches. So refractive index increases, which indicates that it becomes more denser, because after ion radiation, that particular phenomenon of ion radiation actually makes the sample is more denser, rather I can say, and thereby the refractive index actually increases. This increasing trend of refractive index with the ion fluence can be attributed to the SHI induced agglomeration of grains. Thereby, as agglomeration of grains takes place, as a result, it becomes denser. So large grains from forms and with denser packing of structures, which increases the linear refractive index actually. Similarly, the dielectric constant also increases, and the dielectric constant may be attributed to the microstructural modification. Okay, as it is going from cubic to hexagonal structures. This changes in the microstructural modification, it is reflecting in the the values of dielectric constant. In the photoluminescence part, even we have observed changes in the peak position and the intensity as well. The intensity may be related to the quantum yield, but that peak shift is related to the band gap change. Okay, and that has been observed in the case of absorption. That is been observed in the case of orbit and that DFT analysis, and it is as far with the theoretical result. Quantum yield also increases after irradiation, and that is yes, we can say that quantum yield has been observed, and it increases after SHI irradiation, that which indicates that emission is increasing after irradiation process, because there are more defect states are there which contributes to the quantum yield actually. Now in the photometric analysis, we have observed that in the CIE diagram, what happens that we have calculated some coordinates, and it changes its position from the bluish green part to the yellowish green part, and thereafter, after calculating all the coordinates, what happens that we have just calculated the correlated color temperature, and this color temperature, as it is well in the range of 10,500 Kelvin to 5,500 Kelvin, so that may be well suited for LCD and CRT screen, this particular irradiated sample actually. This is a simple idea that may be used, but we directly did not go to the study that whether it can be used for LCD or CRT screen, but this is an indication that it may be used for LCD or CRT screen. Okay, so overall, we can say that SSI is a very good tool to modify the photometric properties of the sample for industrial application. So what happens that in the overall conclusion, I can say that SSI irradiation can modify the CDSC and CDS nanocrystals as I have chosen this material for experimental purpose. We have seen band gap modification, microcellular modification, dislocation density increases, all sort of things which whatever happens in the sample, it is because of the ion irradiation effect, and our theoretical analysis is as far is matching with the UV visible. Experimental absorption and emission spectral part. Okay. And the XRD analysis, which gives some structural modification, structural transformation, it reveals, and it is as far with the Raman spectral analysis also. So our research work is going on. This is in the next phase. We are working on the thermal and electrical properties of semiconductor nanocrystals, and the microstructural modification on the transport properties will be studied, and long and short range order changes because of SHI radiation that can be also studied with after SHI radiation. These are some references. I want to conclude with this. Thank you very much for your questions hearing.
Thank you, Dr. Das, for your illuminating lecture. This term, the period of interaction. I would request the participant to post their questions to the chat box, and Dr. Das is requested, please check your chat box and see, kindly interact.
Yes, I am checking, sir.
Okay.
Uh, okay, sir, I am just checking, but mostly it is related to feedback and other things.
Okay, Dr. Das, please, regarding feedback, I am telling the participant, please give your some feedback to the feedback box, not in the question session. And I would request Dr. Das, since time is short, you
Yes,
please
sir.
select yourself some important questions.
Yes, I am checking.
Highlighting mainly.
Yes, there is a question like after irradiation, will the CDSC and CDS crystals acquire foreign impurities? How does one ensure this does not happen? Actually, you see, somebody asks, yeah, it is from Jagdish Kumar. Yes, Jagdish Kumar. As I have shown you that Siemen team trim analysis, from the team analysis we have chosen the thickness properly so that all the swift heavy ions may pass through the sample. So there is no question of implanting the swift heavy ions in the sample. And as the sample is there inside a vacuum chamber, so we cannot say directly that there is some impurities in that. Even though if you want to check it, whether there is any foreign impurities are there or not, you may check it through EDEX. Okay, so EDEX may give you some foreign impurities, whether it is there, it is implanted or not. But as we have taken the thickness very small compared to the trim after trim analysis part of less than 10 micrometer range, so there is no question of any foreign impurities. Okay. Okay, another question is from Dr. Rajiv Vishwas. The phase change from cubic to hexagonal structure happens at room temperature, or some thermal energy is also involved in this case. See, that phase transformation we can do even by synthesis method also. If you just take some synthesis method, then you can prepare a particular hexagonal structured CDSC or CDS as per your wish. But what happens that that whatever the modification is taking place inside the sample due to ion irradiation, how far the dislocation density will take place, the defect switch takes place, that cannot take place usually without swift heavy ion irradiation or due to the thermal energy. Another is from Dr. Rajiv Vishwas that the phase change from cubic to hexagonal structure. Oh, okay, it is the same question. How do you confirm the lattice change? Yeah, it is the lattice change can be confirmed from the XRD analysis. It is as simple as possible. If you do the readable refinement, you can easily check your data.
I wanted to ask a question.
Yes.
Hello. How do
yes.
you how you prepared your that thin film? What was the technique you used?
See, I went there at USC, and there is a spin coater. So I have used the spin coated material, spin coated method. But we can by drop as the sample is very in the liquid form, it is very in dilute formation. So we can prepare a thin film by casting method also. So
actually the point is that very control over the thickness is required, I feel.
Yes, that control may be the sample preparation may be controlled by spin coater method. That I want to say.
So I think only spin coater can it can be done only over the spin coater only.
Yes,
Because
yes.
controlling is very much essential here. Controlling
Yes,
the theta.
but if you slowly prepare the sample after broadcasting and rolling with the set, that also feasible. But sometimes it never go beyond 10 micrometer range actually.
Okay. Thank you.
Dr. Das,
Yes.
do you want to interact more, or you, if time is not enough, if time is not enough, you can suggest the, or you can tell them that you will give.
Okay, sir. Then I can tell. I want to tell the participant that you contact me directly regarding your question. I can answer it. No problem.
And you give also, please give more 2 or 3 answers. Because
Okay, I am trying to do that. Yeah, I am trying to do that. Yeah, why did the energy of nickel ion chosen so high, 120 MeV? Structural modification are possible in the energy range of a few hundred keV also. Yes, you see in the stream analysis that particular energy, the electronic energy deposition, it becomes flattened after a particular energy level. So we have observed that it becomes almost flattened after 120 MeV energy range, and it may gives you the most electronic energy loss at that particular energy level. So we have chosen 120 MeV. Yes, below that to 120 MeV, it may some sort of structural modification takes place. But what happens that as the electronic energy loss will be less, so your that much structural modification may not you get, may not you achieve, because we have seen that cubic to hexagonal structure transformation is taking place after irradiation or takes place after irradiation. But if you choose the low energy value of ion, low energetic ion, what happens that their fractional change will be less, or some sort of, what if you want one more defects in the sample, then it will be less compared to the higher energy. This question has been asked by Manjurul Khader Ahmed. Okay. Again, the same question. Is there any possibility of reducing grain size of the sample by ionization method? What happens that in general, after ionization, the agglomeration actually takes place, grain size may increase. But there are chances that it may decrease also. There is no question that always the size will increase. Yes, sometimes the size will decrease also.
Dr. Das, please look at another question.
Has electron lattice interaction some influence on electronic and thermal properties of the sample? Is it elastic or inelastic? It is inelastic scattering. It is inelastic scattering. Does this confirm that formation of hexagonal structure requires more energy? Cubic structure are in comparatively lower energy configuration. It is not like that. Sometimes what happens that if you irradiate the hexagonal originally piston hexagonal structures, then some any other particular structural modification may take place after irradiation, depending on the the energy, the sample ion as well.
Okay, thank you, Dr. Das.
Yes,
almost.
Yeah.
And I think it was a nice lecture, mainly to me. I find very nice thing about the sample damage issue and the micro-Raman effect. I think these are to be some issues which new generation should go through. And I also thank to all the participants for their patience hearing. And this is the lunch period. So we will be now away from the venue or the lunch area. Anyway, we will be meeting here just at 2:30 p.m. But participants are requested to come or to be present 15 minutes earlier than the time of commencement of the lecture. That is 2:15. Please give attendance at 2:15. So thanks to all. Thanks to Dr. Das again.
Thank you very much, sir. Thank you very much.
Thank you, Barin sir. There is a small announcement. A test will be conducted at sharply 2 o'clock, 2 p.m. We shall share the link in WhatsApp group. And this is a 10 minutes exam consisting of 10 MCQ. So please don't miss and be ready for that. We shall share at 2 o'clock and the link will be deactivated at 2:10. Thank you very much.